Lesson 11:7, Vision, how your eye actually works. Well, your eye has a lens, and it's a convex lens, a converging lens. The cornea and lens together act as a single thin lens. Cornea is the very surface of your eye, and then behind it is the lens. To see something in focus, the image must be on the retina at the back of the eye, so your rays of light have to converge back there on the retina. The lens can change shape to focus objects from different object lengths. So you have muscles there, and your lens is actually kind of soft, and it can change the shape of the lens. If you're nearsighted, it's called myopia, and the image is in front of the retina, either because the lens is too strong or because your eyeball is too long. That's these up there. You correct myopia or nearsightedness with diverging lenses. I'm going to split the rays of light apart a little bit more so that they meet actually in the back. Farsightedness is hyperopia, and the image is behind the retina, either because the lens is too weak or your eyeball is too short. And you correct those with converging lenses. You bring your rays of light closer together before they hit your eye so that it meets in the retina. So again, myopia, nearsightedness. We put a diverging lens. It separates the rays a little bit more so that they meet at the right spot on your eye. Hyperopia, farsightedness. We put a converging lens to bring the rays together a little bit more so that they meet on the retina. What power spectacle glasses lens is needed to correct the vision of a nearsighted person whose far point is 20 centimeters? Assume the spectacle corrective lens is held 1.5 centimeters away from the eye by eyeglass frames. Okay, so far point here, that means the farthest distance you can see in focus. So you want to bring everything so that it's like it's 20 centimeters away. You want this nearsighted person to be able to see very distant objects clearly. This means that your spectacle lens must produce an image 20 centimeters away from the eye for an object very far away. So we're going to have an object distance of very far and an image distance of 20 centimeters from the eye. Well, an image 20 centimeters from the eye would actually be 18.5 centimeters from the lens. So this distance is 1.5, and the total distance here is 20, so that means this distance would have to be 18.5. Therefore, we want our image distance to be negative 18.5. Why? Because it's virtual. It's on the same side as the lens as the object was. It's on the wrong side of the lens. Our diverging lens only creates virtual images anyway. And our object distance is approximately infinity. The image distance is negative because it's on the same side of the glasses as the object. So our solution. Use our thin lens equation. Our power equals 1 over F equals 1 over DO plus 1 over DI. Now if we're doing power, power has to be in meters. So I used, instead of negative 18.5 centimeters for my image distance, I used negative 0.8185 meters. So this is in meters. All right, 1 over infinity is approximately 0. So that gives us 0, and then 1 over negative 0.185 was negative 5.405. So our power is negative 5.41. That's that. That's that. So he needs glasses that are negative 5.41 diopters. Color vision. Your photoreceptors in your eye are chemical based. You have 2 types, rods and cones. Rods are very sensitive, they see in the dark. However, there's no color information, it's just the intensity of light. It's your more in the peripheral vision. So if it's very dark and you want to try to see something faint, you don't look directly at it, you look beside it so that it shows up in your peripheral vision. The cones are centered in the center of the retina. That's what you look directly at. They work only in bright light, so they don't work when it's very little light. And they do give the color information. So that's why when there's plenty of light, you see lots of color. When it's dark and you don't see much light, you get very little color information because it's really the rods that are working. The cones are not working. Basically, there are 3 types of cones, each one for picking up one of the primary colors. But that's a little simplified. We don't really know exactly the itty-bitty details of how cones work. To see color, you have to actually see light that's coming from the object. So there's that blue surface there. In order to see the blue, you actually have to have blue coming from that object to your eyeball. So if all the different colors hit the blue, and only the blue hits your eyeball, that means it had to absorb the rest. So the object absorbs all the other colors except for the color you see. If it's light producing, then the color produced be the color you see. Some of us are colorblind. If you have normal color vision, you should see a 42. A red colorblind person will see the 2. A green colorblind person will see only a 4. I see a little bit of a 4, so I am green colorblind. If you have normal color vision, here you'll see a 73. If you're colorblind, you won't see anything except for a bunch of little circles. Which is what I see. I see a bunch of colored circles, but I do not see the 73. If you have normal color vision, you'll see a 74 above. If you're red-green colorblind, you'll see the 21. I kind of make that out. Kind of see a 21-ish, sort of. If you're totally colorblind, you won't see anything. If you have normal color vision here, you'll see a 26. If you're red colorblind, you'll see a 6. If you're mildly red colorblind, you'll see a faint 2 as well. I don't see much of anything. If you're green colorblind, you'll see the 2. And if you're mildly green colorblind, you'll see a faint 6 as well. I don't really see anything. How about this one? If you have normal color vision, you'll see a 12. Even if you don't see a 12, you're a liar because everyone sees this. Now, how does color blindness work? There's a mutation in one of the genes that produces proteins in the cones, and so some of the cones don't work right and don't pick up that light as it ought to. But here's where it gets funny, because I'm red-green colorblind. However, I still see red, I still see green. I just can't tell red and green apart when they're next to each other. When they're separate, I can say it's red, I can say it's green. But when they're mixed together, like a stop sign with a big green tree behind it, sometimes I don't see the red stop sign. Also means that often I tell things apart by shape instead of color. I understand that for many people, color is the primary thing to tell things apart. For me, I look for shapes and patterns. Isn't it amazing how the eye works? And yet, they say it just happened. So complex, and no part of it works without any other part. It would all have to come at once, pretty much. So maybe it was designed?